my screen. Okay, cool. I hope that's showing okay. If not, then let me know. So yeah, as I said, as Susan said, my name is Joel Dyer. I'm a DPhil student in maths here at Oxford. I'm going to talk about a working paper that I've released recently with Patrick Cannon and Sebastian Schmon from Improbable, along with my supervisor, Dawn Farmer, here in Oxford. And in this paper, we discuss how two recently developed approaches to approximate Bayesian inference. Sorry, just looking at your message, Susan. Two recently developed approaches for approximate Bayesian inference that have emerged from the probabilistic machine learning community recently are in some ways better suited to the task of Bayesian estimation of ABMs than a number of common approaches in the literature for economic ABMs. And furthermore, give faster and more accurate parameter inferences as well. So in this talk, I'm going to try and summarize our arguments in favor of these methods and hopefully convince you that these methods are useful for calibrating ABMs to data. So I'll first begin with some context. There we go. Begin with some context and talking about ABMs. So if anybody isn't familiar with ABMs, they are computer programs that are simulation models. They consist of interacting autonomous heterogeneous decision-making entities that are the agents of the model. And it's important for our setup to say that these models are usually stochastic, such that running the model multiple times at the same parameter settings will give you different outputs. And using ABMs can be really good because they allow modelers a lot of flexibility, because you don't have to worry so much about analytically tractable, developing analytically tractable models anymore. And by building these complex virtual systems and simulating from them, you can study complex systems and emergent phenomena, non-equilibrium systems more easily than modelers have previously been able to do so. Also, they naturally allow for interactions and heterogeneity across agents, so and do so more readily than alternative modeling paradigms. So those are some reasons why ABMs are really good. But to actually use them to do applied research, we need to be able to fit the parameters, which I'll denote with a theta throughout this talk, to observe data from the real world, which is something I'll denote with boldface y. Or in other words, we want to be able to perform parameter inference for these models. And importantly, as we said before, we want these parameter inference techniques to take into account the fact that these models are stochastic in nature. And traditionally, a natural choice of approach for performing inference with stochastic generative models is to employ likelihood-based approaches. For example, to employ Bayesian inference, which involves writing down this prior density here, P of theta, which captures your initial beliefs on the appropriate values that theta could assume, the parameters could assume, and then to use Bayes' theorem in equation 1 here to invert the generative process and find a posterior density, P of theta given y, which then encodes your updated beliefs about appropriate values for theta. And so Bayesian approaches are what we're going to consider in this talk. And the reason that we focus on these is that we take the view that it offers a lot of benefits, such as a natural approach to uncertainty quantification via the posterior density, its ability to incorporate prior knowledge about the world via the prior P of theta, and also the fact that it's, I personally think, and I think a lot of people would agree, that you can make more intuitive probabilistic statements about the inferences you draw using Bayesian inference to non-technical decision makers, and that's important when you want to use these models in the real world with as I say, non-technical decision makers. So those are the reasons why we're going to stick to Bayesian methods in this presentation. And so we want to do Bayesian inference, but the problem of performing Bayesian inference is complicated by the fact that ABMs, as with many simulation models, have intractable likelihood functions in general. And this is usually because what one observes often is some aggregate data describing the state or the evolution of the system, which is this boldface Y, while the states of the agents in the system remain unobserved throughout the dynamics of the system. And so evaluating the likelihood function involves having to integrate out these agent trajectories, and that's a very high dimensional integral that's hard to compute. So, this clearly causes problems for a lot of inference techniques that are based on likelihood, evaluating the likelihood, both in the Bayesian framework and in frequentist framework, for example, the maximum likelihood estimate. And so, in both of these cases, what we want to be able to do is evaluate the likelihood on a point-weight basis for all given theta, if not write down a closed form expression for it to make immediate use of these methods. But we can't do that. So the question that we're left to ask is, how do we proceed with statistical inference when we don't have access to the likelihood function? And one possible answer to this is to use likelihood-free simulation-based inference techniques, in which one simulates from the model at different parameter values to try to determine which parameters could plausibly have generated or claim responsibility for the data set that we actually observe in the real world. So that's what we're going to think about now. And this field of simulation-based inference is a fairly big one in computational statistics, and a number of approaches that exist in that field have been adopted in the economic agent-based simulation literature already. And very broadly, these Bayesian simulation-based inference methods proceed in a fairly similar pattern, which I'll take you through now. The first step is often something like pick a parameter value to test, theta1 here, for example, by proposing it from the prior density. Then simulate a bunch of different data sets at that parameter value, which are these different time series here, this red, blue, and green one down here. Then to use these simulations to construct some estimate of the likelihood function at the observed data and at theta1. This is what this P of hat given, P hat of Y given theta1 is here. And then to use that estimate of the likelihood function to find some estimate, possibly an unnormalized estimate of the posterior probability density at theta1 given the observed data set Y. And then, this is one step in the procedure, but then by repeating this step over a bunch of different parameter values, one can slowly build up a view of the posterior density by repeating that procedure at lots of different parameter values. So this is broadly how many of the most popular approaches to simulation-based Bayesian inference proceed in the economic ABM literature. And in many cases, the key difference between these is just how the likelihood function P of Y, P hat of Y given theta is approximated or constructed using these simulations at each parameter value. For example, so I've listed some here. For example, Grazzini et al. There's a fairly big and well-known paper by Grazzini et al. On Bayesian estimation of ABMs that they released in 2017 or had published in 2017. In which they consider different ways to approximate this likelihood function. For example, one approach that they considered was to treat the observations in the time series generated by the ABM as being essentially identically and independently distributed, and then to fit a kernel density estimate on that set of samples to construct a likelihood approximation. However, there are other ways that people have done so, and I've listed some here, and also in our paper we summarize fairly comprehensively, I think, the different approaches that people have taken to approximate the likelihood function for an ABM. So what I'm going to do now is try to argue that these existing approaches to Bayesian parameter inference for ABMs are suboptimal for a number of reasons. And to do so, I'm going to give two main reasons why parameter inference for ABMs can be particularly hard compared to inference for other types of simulation models. So first, consider the fact that ABMs are often used in economic settings to simulate the actions of and interactions between many agents in a social system. And to make such simulations high fidelity, one must sometimes simulate a large number of agents. And so, for this reason and for other reasons, ABMs can be very expensive to simulate. And this throws up clear problems for inference techniques that rely on the experimenter's ability to simulate from the model repeatedly and sufficiently many times to construct an accurate picture of the posterior density. Second, ABMs are often used to model the evolution of a social system and emergent phenomena in a social system. And for this reason, ABMs can generate high-dimensional, possibly multivariate and otherwise complex time series that exhibit complex dynamics that are difficult to model. And often the reason that one resorts to ABMs is that these sorts of data that we're trying to, the sort of data that we see in the real world is often hard to model with other methods. So bearing these two difficulties in mind, many approaches to simulation-based parameter inference, such as the ones that we outlined earlier, are poorly suited to ABMs for two reasons. The first is that they require a large simulation budget, a very large simulation budget, in order to achieve an acceptable Monte Carlo error on the approximate posterior. And so, if you recall from the methods that I outlined earlier, many involve simulating multiple times at each parameter value tested. And then you must also visit many millions of parameter values to fully and properly explore the parameter space with a fine enough resolution to build a sufficiently accurate picture of the posterior density. And since there's no sort of mechanism for sharing information between each point-wise estimate of the posterior density, this ends up being a very simulation-heavy approach to approximate posterior inference, which can be prohibitive when you have very expensive ABMs, and this is often the case with ABMs. The second reason then is, they are sometimes poorly suited to ABMs, is that many of these methods attempt to construct explicit models for the likelihood function of the ABM. In other words, they try to construct something like a meta model or some approximation to the likelihood function that can be used both as a way to evaluate the likelihood function and to sample from it. And the reason that an approach like this is poorly suited to the problem of calibrating ABMs is that, as we discussed earlier, ABMs are often by design, they often by design generates complex non-equilibrium, non-linear dynamics that are hard to model. And as I said, this is often the reason that one resorts to ABMs is that because that sort of data is hard to model, you resort to complex high-dimensional systems with many agents interacting with each other. So to take an approach that involves constructing an explicit meta model for the ABM is to assume a quite difficult task of modeling this complex time series data. And it's easy to fail at this task because it's easy to construct, and it's easy to fail at this task because the data is hard to model, and in that way it's easy to construct ineffective inference procedures by focusing on approximating the likelihood function. And in any case, even if the time series being generated were simple, the fact that they are benign in terms of their complexity, the fact that they're high-dimensional time series data, it still means that it's a hard computational task to model the density of a high-dimensional data set. So for this reason, many of these approaches that involve focusing on estimating the likelihood function, they need to make simplifying assumptions such as I mentioned earlier, independent and identical distributed observations in the time series, which by doing so, you destroy important information in the data, such as the ordering of the data and the fact that there's a non-trivial dependency between the different observations in the data set. So those are some of the main reasons why existing parameter inference techniques in the economic ABM literature are often poorly suited to the task of calibrating ABMs. So with this in mind, we can say that better approaches to parameter inference for ABMs would ideally involve reducing the simulation budget to something more manageable for expensive ABMs. They would refrain from attempting to model the distribution of the data itself, which is, as I said, a difficult high-dimensional task, density estimation task, especially due to the nature that of the data that arises in ABM settings. And finally, we would like methods that refrain from imposing inappropriate or restrictive assumptions about the data or the form of the simulator, such that the models remain faithful to the form of the data that they're generating or being calibrated against. And the reason so we want some like generically applicable black box approaches to inference. So these are three qualities that we like to look for in an inference procedure, and three ways that we think existing parameter estimation procedures that exist in the ABM literature can be improved upon. So what I'm going to try to demonstrate to you in this talk is that two relatively new methods that have emerged from the probabilistic machine learning community, called neural posterior estimation and neural ratio estimation, are equipped with those three qualities that I described in the previous slide. And therefore, they are also equipped with the potential to address some of the shortcomings in the ABM estimation literature. So what I'm going to do for the rest of the talk is tell you a bit about the idea behind how these two methods work, and furthermore, some of the results that we've been able to achieve for them so far, and other arguments in their favor. So the first of these is called neural posterior estimation. And the idea behind this is to use a conditional density estimator to model the posterior density directly. So that is to learn a function of two inputs, x and theta, that provides you with a non-negative real number estimating the posterior density at that point, theta x. And there are multiple ways to do this, but one possibility and one common possibility is to use what's called the normalizing flow. So for normalizing flows, this particular approach involves, the idea is to construct a sequence GI, so a sequence of functions GI that are invertible and differentiable and have inverses Fi. And these functions transform a simple base density, for example, a standard Gaussian density, from the standard Gaussian density through each of the functions into a more complicated probability density function. And so, as you can see, if you follow these green arrows on the top, what happens as you pass samples from the base density through each function, you slowly morph the distribution into something more complicated from the original simple base density. Furthermore, since the functions GI are invertible, density evaluation is a simple matter of passing your data, your observation in the real world, backwards through this flow to find the point in which it exists in the original space, and then applying this, the standard change of variables formula in probability theory to evaluate the density of that point. So in summary, using a normalizing flow for this conditional density estimation task, when using this, sampling from the approximate posterior entails sampling from the base density and propagating forward through these layers, and then subsequently evaluating the posterior density entails just applying this change of variables formula to in equation 3 here. And just to say quickly how these functions GI are found, they're typically constructed with a neural network and learn from data. So just to loop back again and consider this approach, and how this approach provides benefits over the existing methods I outlined in the beginning of the talk, I'll just say about how it meets each of the three desirable criteria that we listed earlier. So the first desirable criteria that we considered was that inference entails a limited simulation budget, because ABMs are often very expensive to run. And the reason that this approach meets this criteria is that it learns a posterior density estimator globally across the entire space of data and parameter pairs. And in this way, the conditional density estimator can share information between points in that joint space, and in that way learn more efficiently from a given simulation budget. And this contrasts with a number of these existing approaches in which simulations generated at a parameter value theta only contribute to the posterior density estimate at that theta. Furthermore, then, once the density estimator is trained, no further simulation is required from the ABM to construct a posterior density. And this decoupling of the task of posterior construction from the task of simulation also helps to reduce the simulation budget involved with constructing a parameter posterior. The second desirability criteria that we considered was that the inference procedure refrains from modeling the data distribution itself, or refrains from performing a meta modeling of the ABM, which we argued was a difficult task due to the complexity of the time series that the ABMs generate and the dimensionality of the time series. Also, the fact that time series are potentially multivariate and long. And the NPE approach, this neural posterior estimation approach, clearly refrains from trying to model the density of the data, because it goes straight to modeling the posterior density directly, rather than first approximating the likelihood and then using Bayes' theorem to get the posterior density. So it meets that second criteria as well. And then finally, the third desirability criteria was that the inference method refrains from making rigid or unsuitable assumptions about the form of the simulator or the nature of the data that it generates. For example, by assuming that the observations in the data are identically and independently distributed. And the reason that we want to avoid doing that is that it remains then applicable generally to different types of models, or doesn't invalidate the inferences drawn about the parameters by introducing inappropriate assumptions. And I guess in the interest of time, I won't go into the exact details about how to construct the neural networks that model this function. But the upshot is that this method can flexibly handle data of different kinds, including high dimensional time series data, by choosing an appropriate neural network architecture, for example, by just passing the time series through a recurrent network of some sort, and doing so here where this embedding network box is placed. So the embedding network takes in the time series and then sort of prepares it in a form that could be passed into this conditional density estimator. So in this way, this approach can flexibly accommodate different data types without making any simplifying assumptions or inappropriate assumptions about the form of the data for the sake of tractability. So that's the basic idea behind NPE, and how. Oh, I see Heido, and you've raised your hand.
Yeah, is it okay? Do you want to take questions as you go along, or would you rather wait to the end? I guess maybe you could say a little bit about how do you vary the parameters, because you've got to search through the parameter space to do this, right? So you have to have some sensible. I mean, usually in a search, you spend a lot of time thinking about, okay, I tried this one, it was that close, let's try another parameter value. Now you want to generate the whole likelihood function. So that's as a function of the parameter and the state that you're in both. So the state, I mean, if you march along the time series, you have lots of states. You kind of know a priori which states you care about, but which parameters you care about isn't so clear to me. So maybe you can just say a bit about that.
Yeah, well, from here, okay, so from here, looking at this figure 1 again, the way that this NPE approach works is that it transforms this simple Bayes density, as I said, a standard Gaussian is a common choice, into something more complicated. And the target distribution, which is the more complicated distribution, is the posterior density. And so the way that it knows which parameters are interesting is just by design of the method. It learns these functions and how to map points in this original space on the left here over to the right. It learns how to transform it into the more complex distribution.
So I understand that, but I guess the part I guess maybe to try and answer my own question, it restricts itself to parameters that allow it to, that have outputs that correspond to the actual observed states. And now, I mean, because in the picture you show, you're just showing as an X, right? But you've got to at least have a theta. So it's at least a two-dimensional space. And the thetas that it's going to explore are going to be thetas that allow it to actually reproduce X.
Yeah, so I'm going to apologize for the figure because it is a bit misleading, and in that I'm not showing a conditional density estimation. I'm just showing it in generality, but it's just by showing the network pairs of data parameters, and whether the data is generated by the parameter, it just learns then how to assign mass in the final density, just by learning which parameters are sort of plausibly responsible for data that you observe.
Great, thanks.
Okay, thanks, Don. So I think I finished this slide. So next I just wanted to say what neural ratio estimation was about, and the idea behind it. And in this case, it's slightly different in the sense that here we're using, the idea is to use probabilistic classifiers to learn density ratios rather than straight densities. For example, a ratio that is of interest in the scenario of Bayesian inference is this ratio between the posterior density and the prior density. And well, I'll say why it's of interest in a sec. But the way that one can go about doing this with probabilistic classifiers is to train this classifier to distinguish between two sets of data. The first is a set of data that consists of data parameter pairs, so x and theta, that are drawn from the joint density for the model. So generate a parameter value from the prior, simulate from the ABM at that parameter value, and repeat that over and over again. So that's one data set that is given. The other is a data set that is drawn from the product of the marginals, and given it a different label. And the way to understand the second data set is that whereas in the first, the data x pertains to the parameter to which it's paired, in the sense that the parameter generated that data set. In the second, on the right hand side, it's all mixed up. So the data, the x's, don't pertain to the parameter theta, in the sense that they weren't, that theta didn't generate that x. That's what I try to show here with the different colors. So there's no relation on the right hand side between the x's and the thetas to which they're paired. And so the reason that this is interesting and useful for the problem of Bayesian inference is that when you train a probabilistic classifier to distinguish between these two data sets, the classifier learns to estimate this class 1 probability, which is highlighted in blue here, which is the ratio between the joint density to the sum of the two possible, the joint plus the product of the two marginals. And so it attempts to learn that probability, and once it's learned that probability, you can, just with simple algebra, rearrange this such that the logic of this d function here in equation 4 gives you the log of the ratio between the posterior density and the prior density, which then clearly allows you to evaluate the posterior density by taking the exponential of the logic and multiplying by the prior density. So that's the idea behind neural ratio estimation. And once again, the reason that neural is thrown in here is that neural networks are often used to perform this classification task. So now, before I show you the sort of results we've had with these different methods, I'll just first say again why it is that NRE, neural ratio estimation, meets the 3 desirability criteria that we stated earlier. And it does so in much the same way that NPE did when we discussed it earlier. But in summary, it helps to reduce the simulation budget by training a single density ratio estimator across the entire space of data parameter pairs. And by doing so, it enables this sharing of information that I talked about earlier. Whereas, as I was explaining earlier, the existing methods that I outlined at the beginning of the talk they have no mechanism for sharing information between posterior density estimates. Simulations at parameter theta only contribute to the density estimate at theta. The second reason that the second way that it meets our desirability criteria is that it once again refrains from estimating the likelihood function or constructing an explicit meta model for the ABM, and instead assumes the simpler task of discriminating between x theta pairs rather than attempting to generate x given a theta. And this is, well known in both machine learning and in, I guess, like human neuroscience, that humans and computers alike find discriminative tasks easier than generative tasks. Humans and computers alike find it easier to distinguish between images of cats and dogs than they find it easier to distinguish between images of cats and dogs than they find it to actually draw pictures of cats and dogs. So that's why it addresses the second point. And the third way that it addresses the desirability criteria is that it once again refrains from simplifying assumptions about the data and about the ABM in much the same way as in NPE, in that it can accommodate data of different types by just choosing an appropriate neural network architecture for the classifier. So once again, if it's a time series, you can stick in a recurrent neural network of some sort here to account for the fact that it produces a time series as output. So that's sort of an overview of how they both work. And to just come to the end of the talk, I'll tell you a bit about how they work and how they perform in comparison to popular alternatives in the economic ABM literature. And I'll end with a final point about how they can be helpful in real-world settings too. So in our experiments, we focus on comparing against the most flexible and automatic method that Grazzini et al. Describe in their 2017 paper on Bayesian estimation for ABMs, which a fairly recent paper by Donovan Platt, who was previously a doctoral student here in Oxford, showed could outperform a broad range of alternative inference procedures in a variety of settings. So, and just to say, I'll refer to this as KDE, the Grazzini method as KDE in the rest of the presentation. And just to say also that furthermore, since our goal is to perform Bayesian inference and to get a full posterior out for the parameters, we're going to assess the ability of these different methods assess the ability of the performance of these different methods by assessing how well they recover the full posterior shape in cases where the posterior is available, the ground truth posterior is available. And that's important to do because we want to be able to correctly capture the uncertainty in the parameter estimates. And that's the benefit of the Bayesian approach to inference. So the first experiment that we consider is a standard test case example in the economic ABM estimation literature. It's a model developed by Brock and Holmes, describing, if I remember correctly, the price of an asset. And they do so by modeling the behavior of fundamentalist and chartist investors trading in a market. The model here generates a univariate time series and has four free parameters that we want to obtain the posterior density estimate, posterior density for. And furthermore, this model has a tractable likelihood function. So in this case, we can compare the approximate posteriors that we get from these different methods against the ground truth posterior, which is what I show up here in the top left-hand corner. And just to say how to read these plots. So in each of these figures, the diagonal consists of the marginal densities for each of the parameters, while the off diagonals are the joint bivariate densities for each pair of parameters. So So that's the ground truth posterior there. The remaining figures are the Grazzini KDE posterior up in the top right-hand corner. And then on the bottom row, there's the MPE posterior and the ratio estimation posterior that we get with these two methods that we're advocating for. And as you can see, the ground truth posterior density up here in the top left shows that the marginal posteriors we get out for the second and fourth parameters are quite sharply focused on the posterior means, and are far more broad in the first and third parameters with some bias to the left. And so we're looking to be able to reproduce that with the posteriors that we get from the approximate methods. And so by looking at the KDE posterior, we can see that it doesn't quite manage to get many of these right. So for the second and fourth dimensions, they're biased and are not so sharp on the correct values. And furthermore, the bias in the first and third dimensions isn't quite there. But in the case of NPE and NRE in the bottom row, we see a lot that these features are pretty much captured. So in the second and fourth dimensions, the marginal posteriors are quite sharp on the ground truth posterior mean, and similarly in the first and third case, the bias to the left is also somewhat present, not fantastic in this third case, but definitely somewhat present. And finally, also by looking at the joint bivariate densities on the off diagonal, they look quite similar to what you get in figure 10 from the ground truth posterior, whereas in the case of the KDE posterior, the off diagonals match the ground truth off diagonals far less closely. So visually, NPE and NRE here look quite a lot better than KDE does. And just to say too, that gap in performance, that increased performance with NPE and NRE, that's present despite the fact that they use 10 times fewer simulations than the Grazzini KDE posterior. The Grazzini KDE posterior involved 10 to the 5 simulations, or was provided with a 10 to the 5 simulation budget, whereas the NPE and the NRE posteriors, or NPE and NRE, were afforded a budget of 10 to the 4 simulations. So that increased performance is present despite that disadvantage. And just to say too, that I won't go into detail with this table, but the enhanced performance isn't just apparent visually when you compute popular posterior quality metrics that appear in the approximate Bayesian inference literature. You also see that the metrics are better for the MPE and NRE posteriors than they are for the KDE posteriors. So that's one experiment. In the next experiment, we consider not an agent-based model in this case, but a multivariate geometric Brownian motion. And the reason that we stray from an agent-based model in this case is just to demonstrate how these methods perform with multivariate simulators. So as I say, this is a model that generates a multivariate time series as output. And once again, we've got the ground truth posterior up here in the top left corner, the KDE posterior obtained from the Grazzini paper in the top right, and in the bottom row, we've got MPE and NRE posteriors. And the conclusions from this slide are much the same as in the previous slide. So if you compare the true posterior to the NRE posterior and the NPE posteriors, they're actually almost indistinguishable. Whereas when you compare the true posterior to the KDE posterior, despite the fact that the KDE posterior in this instance uses 1,000 times more simulations than NPE and NRE did, it's a far worse approximation to the ground truth posterior. For example, this second marginal density assigns practically no mass, no density to the ground truth posterior mean, whereas it should have a relatively high posterior density. So not much more to say about that, but just the fact to highlight once again that this discrepancy in the performance is also present in popular posterior quality metrics that are used in the approximate Bayesian inference literature. And once again, this is present despite the fact that NPE and NRE uses only 10 to the 3 simulations, whereas KD uses 10 to the 6. So quite a big gap in performance. Now, I hope that sort of demonstrates how well these methods can work. Just to spend another 5 minutes on how these methods can be really helpful in real-world settings. We've seen in the previous two experiments that where we put a ground truth posterior to compare against, NPE and NRE perform strongly and get accurate posteriors. But in the real world, clearly you don't have a ground truth posterior to compare against. That's the reason that you use these approximate techniques. And you often find yourself in a situation where you generate an approximate posterior density, and you plot it out, and you take a look at it and you think, how do I know whether this is a good posterior? And how do I know that I've correctly captured the uncertainty in the parameter estimates? And this is a question that Bayesian statisticians ask themselves all the time, and they've developed some tools for this. And one such powerful tool is called simulation-based calibration. And this is developed and reported by Taltz et al. In reference 9 here. And the idea is that, very briefly and roughly, to construct many different posteriors and then to average them all. And what you should get in return if you do that is the prior, which you specified in the entire inference procedure. And this is the case because of this identity here in equation 5. So the idea behind simulation-based calibration is that if you go through this procedure where you construct many different posteriors from many different data sets, take the average of them, and then what you can do at the end is look at how well that average corresponds to the prior that you actually specified. And so checking for the self-consistency helps us identify how well our approximate posteriors are, or how good our approximate posteriors are, and also the specific ways in which they are bad, if they are bad. And I'd refer you all to the Taltz et al. Paper for more details on how that's the case. But as I mentioned, doing this, using this good method, entails constructing many different posteriors over many different data sets. And so if your posterior construction method is one of these existing ones that I mentioned earlier in the talk, where you must perform millions of simulations to construct the posterior, then trying to take advantage of these posterior quality checks quickly becomes infeasible and requires an immense simulation budget. But in contrast, with NPE and NRE, the simulation budget required to perform the simulation-based calibration is just a tiny fraction of what it would be with those other methods. And the reason being that, as I said before, NPE and NRE decouple the act of simulation from the act of constructing posteriors, because they train density estimators upfront that can be used later to evaluate the posterior density and sample from it. So the point of this all is just to say that, as I say, I can't go into detail because in the interest of time, but not only do NPE and NRE show good performance in recovering single posteriors with a far lower simulation budget than alternative approaches, they also then bring into the realm of possibility these methods that allow us to check how good our posterior inferences are in real-world settings when we don't have a ground truth to compare against. So, not only are they fast and accurate methods, but it also helps us identify whether or not our inferences are accurate and give us some confidence in whether these inferences are accurate. We explain this a bit more in our paper, so please take a look at that if you are interested in reading more. But that's practically everything that I wanted to talk about. So just to summarize and conclude, in this talk, I gave an overview of the broad procedure by which many existing Bayesian inference methods proceed in the ABM, in the economic ABM literature. I try to highlight some of their shortcomings, for example, the fact that they entail a high simulation budget and are focused on likelihood estimation, and why these are difficult, these are problematic in the case of ABMs. I then gave an overview of what NPE, neural posterior estimation, and neural ratio estimation are, and why they might be good alternatives to these different approaches, these existing approaches in the literature. And we demonstrate with experiments that they quite easily outperform some of the, what would I think be considered some of the state-of-the-art methods in the economic ABM literature, despite having a far reduced simulation budget. And then finally, in the previous slide, I discussed how NPE and NRE bring into the realm of possibility these posterior quality inference checks, thereby helping you to be more confident in your inferences in real-world settings. So please check out our paper if you're interested. And thank you for coming to the talk, and happy to take any questions.
Wonderful, thank you very much, Joel. So yes, if anyone's got any questions, just feel free to turn on your camera or raise your hand or unmute and ask away. Thanks very much.
So Joel,
Hi.
Do you want to say something about scaling up? I mean, do you think, how optimistic are you that you'll be able to do problems where you have 10 or 30 free parameters rather than just say up to 4?
Yeah, good question. I'm more optimistic about, the short answer is that I'm more optimistic about density ratio estimation than I'm about posterior estimation. And the reason is that in the case of neural posterior estimation, I mentioned that the way that it works is that it entails constructing an explicit model for the density in the parameter space. And as the dimensionality of the space that you're trying to model increases, so does the difficulty with which that, so does the difficulty of that density estimation task. So that's one reason why it probably will become more difficult to model very large parameter spaces with neural posterior estimation. With neural ratio estimation, on the other hand, there's no attempt to model the density of the space explicitly. It instead performs this discriminative task where you say, I give you a data and a parameter, tell me the probability with which you think the data pertains to the parameter. And given that it discriminates and conditions on the parameter as well as the data, in that case, I think that's a more promising avenue than posterior estimation, where it tries to model the density in the high dimensional parameter space directly.
Yeah, that's a really nice, can you make any nice examples or anything to show, maybe it's just a suggestion, it'd be nice to have a nice example to show how you get dimensionality reduction by doing that, because I think that's the key thing. And I guess you're hoping that because you're dividing by because you're dividing out the P of theta, that you're going to get lower dimensional object as a result.
Yeah.
Somehow, yeah, go ahead.
No, I think you're right. I think it would be in a later iteration of this paper, it would be really good to try and explore that idea, whether it's what we were just saying really amounts to an easier task with density ratio estimation than with posterior estimation. Hey Ernesto, I see you got your hand up.
Hello there. First of all, that's a great presentation. And I only have two, I suppose, very small questions. One of them is more about, you compare yourself to KDE and that's fine because the examples you show and you present that paper, but it's sort of like, sometimes feel like you're taking candies from a baby, like KDE sometimes work very well, but it's surprising when it does, right? I don't know exactly the NP you used. There is a there's a Python package called SBI, which implements some of them. In my experience, they're okay, but not amazing in calibration, especially point predictions where the parameter actually was. And so I'd be curious if you compare this to maybe something like, maybe random forest ABC or neural network ABC, just to get an idea, how often it actually performs better. Like my idea really is that, sometimes NPE, well, those are sequential NPs, so it's slightly different, but whether sequential NP or sequential NRE perform better, if I had to, my guess would be they perform better sometimes, but I don't think they're gonna win every possible example. If you show a paper with enough examples, maybe something like Sugarscape or Schelling would be nice, because those are 4 or 5 parameters, right? So slightly above what you have now, but everybody understands them. So I'd be very curious to see if they beat the ABC, modern ABC stuff. And the other thing I wanted to say, sorry, then I'll let you talk, is I really like the point you make in the very last slides there, or the second last, I suppose. NP as amortization, which makes all sorts of diagnosis, all sorts of self-validation sort of easier, right? Because you don't have to retrain it all the time. And that's a very clear, very important point. A lot of people forget. It's really important to explain, to prove to yourself that the calibration method actually works. But one thing that, and I do this, I don't have a solution, but what I'm trying to say is we can prove that if the data come from the model, we can find the parameters that generated it, right? That's fundamentally what we're trying to validate. However, we also know that the model is wrong. So how will we go about saying, just because this method is better at re-recovering its own parameters, does that mean that we'll actually, when we calibrate to real data and therefore to something that doesn't come from the model, how do we know that these are actually the best parameters for what we're trying to do? Like, it seems like we're good at this necessary condition of self-diagnosis, but it is not clear to me that if we were to use something very naive, like just, a minimization, we're trying to match a curve. If we were to do it on real data, which doesn't come from the model, that would generate something worse. That's really where I'm at. I just want to pick your brain on.
Yeah, no, absolutely. And so I'll try and work backwards, but, the point you raised about misspecification and the fact that, your model is going to be wrong when you've got real data, it's just a problem for all inference methods, as far as I know. I'm not sure. I mean, I know there's a lot of active research going on at the moment with robustifying inference procedures to this problem of misspecification. And as you say, it's convenient in the simulation-based inference literature, or any, I guess, inference literature, to just ignore that that's a problem and say, let's just see how it does on data generated by the model. And yeah, I mean, I'm not sure that I can really say much else apart from that I agree it's a problem. I think there's one of my colleagues is, I think Patrick, maybe would have something to say about that if he was here, but I'm not sure that he is here. But it's certainly a problem. Some of the things you were saying were, you were talking about how well they recover like point estimates and that sort of thing. I guess a comment that I have in response to that is that for a finite data set, you wouldn't necessarily expect that the posterior would even assign a high probability density to the frequentist ground truth. It's only, I think the results only exist asymptotically for infinite data set, and I think possibly even IAD observations. I'm not sure that I'm not sure whether results exist for sequential data, but maybe they do. But I think in any case, for a finite data set, you wouldn't necessarily expect that your generating parameters are going to be assigned a high posterior density. That's my response to that. Did I cover everything, or was there anything else there?
Yeah, that covers it. Thank you.
Yeah, thank you. If anybody else has got any questions, then feel free to raise your hand.
Yeah, I'll just second that. Is there any other questions? And if not, we might wrap up. No, it's looking like I think we've covered it all. Wonderful. Well, thank you very much, Joel. And as I said, yes, if anyone wants a link to the recording, just let me know. And I think that's it for this week. And hopefully we'll see you all at other events in the following weeks.
Yeah, thank you, everyone.
Lovely. Thanks very much, Joel. Bye, everyone.
Bye.